Did everyone hear his question? Each pair of lab partners will turn in just one video. One video. Make sense to everyone? Okay, cool. So let's get started on today and get you back into that lab. He's looking around as soon as possible. In your workbooks, everyone. On page 193. We'll use them again. One 93. Thank you. It says here, acids and bases have been known for a long time. When Robert Boyle characterized them in 1680, he noted that acids dissolve many substances, change color of certain natural dyes. For example, they change litmus from blue to red, and lose these characteristic properties after coming in contact with alkali, which we now know are bases. That was a long time ago, 1680. 1680. In the 18th century, it was recognized that acids have a sour taste. These don't taste anything in lab. They react with limestone to liberate a gaseous substance. They didn't know what it was, but now we know it liberates carbon dioxide. And interact with alkalis to form neutral substances. Okay, that's kind of cool. In 1815, Humphrey Davy, that's the name, Humphrey Davy, contributed greatly to the development of the modern acid-base concept, modern at that time, by demonstrating that hydrogen is the essential constituent of acids. Around the same time, Joseph Louis Gay-Lussac. Sounds familiar, right? Gay-Lussac? Well, you guys watch the videos? No? Okay. Around the same time, Joseph Gay-Lussac concluded that acids are substances that can neutralize bases, and that these two classes of substances can be defined only in terms of each other. That's just romantic. Yin and yang, right? You can only define them in terms of the other. The significance of hydrogen was re-emphasized in 1884 when Arrhenius defined an acid as a compound that dissolves in water to yield hydrogen cations. Now we call hydrogen cations hydronium ions. And a base is a compound that dissolves in water to yield hydroxide ions. So from all of that, what are we going to write down for notes? Well, one guy we need to know is Arrhenius. A-R-R, right? Arrhenius, and he described an acid as what? Okay. Dissolves in water to yield hydrogen cations. Okay. And what did he say was a base? Okay, Arrhenius base. So compound dissolves in water, and compound dissolves in water. This one yields hydrogen ions, and this one yields hydroxide ions. Make sense to everyone? We good? Okay, let's keep going. Acids and bases are common solutions that exist everywhere. They have opposing chemical properties, romantic yet opposing, and are able to neutralize one another to form water, which will be described in later subsections, very important. Acids and bases can be defined by their physical and chemical observations in the table below. This is what you guys have been learning since kind of middle school. Taste sour versus bitter. What's the difference between sour and bitter? Bitter makes you want to gag. Bitter makes you want to gag. It's actually a location of where the taste buds are on your tongue. Bitter, you're more likely to ingest. Okay, cool. So you can read. Okay, acids and bases in aqueous solutions will conduct electricity because they contain dissolved ions. Therefore, acids and bases are known as electrolytes. Strong acids and bases behave as strong electrolytes versus weak acids and bases behave as weak electrolytes. A strong electrolyte, the light bulb's really bright. A weak electrolyte, the light bulb's dim. Remember the light bulbs? Okay, cool. In chemistry, acids and bases have been defined differently by 3 sets of theories. First is the Arrhenius theory, which we just went over, which relies on the idea that acids are substances that dissociate, break off in an aqueous solution, that's the whole water thing, to produce your hydrogen ions, and bases produce hydroxide ions. So that's what we already talked about. The other 2 definitions include the Bronsted-Lowry definition, which we're going to get to, which defines an acid differently. It defines an acid as a proton donor, and bases are proton acceptors. So we got Arrhenius. Let's do Bronsted-Lowry now. And that is the Bronsted-Lowry acid. And a Bronsted-Lowry base. What does Bronsted-Lowry call an acid? Okay. Proton donors. And the proton he's talking about, H plus donor. And the base is a proton acceptor. Proton acceptor. So notice there's no mention of hydroxide in Bronsted-Lowry. And we also don't have this water requirement in Bronsted-Lowry. We don't have the water requirement like we did with Arrhenius. Water requirement. As shown in the figure below, the level of the theory expands to include more substances covered under each definition. The closer the theory comes to accurately describing the actual acid-base chemistry, and we are not there yet. But if we look at this, if you think back in time, that was Arrhenius, then it got a little bigger with Bronsted, and then the Bronsted-Lowry. And then the biggest one currently is Lewis, and know that your kids will be probably taught another one, right? As science builds on itself. So looking at this Venn diagram representing the 3 levels of acid classification theory, Arrhenius theory is the least accurate, but it's still a tool, and covers the smallest subset of substances because they have to be dissolved in water. Bronston-Lowry expands on Arrhenius definition and thus slightly broader. And then the Lewis theory is the most extensive explanation and most accurately describes all acid-base behavior that we know of right now. Let's not go a little nuts. So this is an example of an Arrhenius acid compound. HCl, we know that as hydrochloric acid. And if we look at Arrhenius, it says in solution in water. That's why we're aqueous, right? An acid is anything that increases the hydrogen ion concentration, right? It dissolves in water and yields hydrogen ion. So this dissolves in water and yields hydrogen ion, Arrhenius acid. Arrhenius base dissolves in water and yields hydroxide ion. So this is an Arrhenius base. Sodium hydroxide, aqueous means it's in water. And yeah, it gets the sodium ion, but we're just looking at that base. That makes sense why it's Arrhenius? Okay, cool. Cool. As you can imagine, this Arrhenius level of theory is quite limited. The Arrhenius definitions of acidity and alkalinity are restricted to aqueous solutions and refer to the concentration of solvated ions. That means only the ones that dissolve, right? Only the ones that dissolve. Under this definition, a solution of pure, what's this called? Sulfuric acid or hydrochloric acid dissolved in toluene would not be considered to be acidic. So both of these, if it's not dissolved in water, according to Arrhenius, would not be acidic, right? If they dissolve it in something like toluene, despite the fact that both of these acids will donate a proton to toluene. So because it's not in water, it wouldn't be considered Arrhenius. In addition, under the Arrhenius definition, a solution of sodium amide right there, in liquid ammonia is not alkaline, despite the fact that the amide ion will readily deprotonate. That means basically take a proton, deprotonate, take a proton from ammonia. NH2 is going to take a proton to make NH3, right? It's going to want to do that. So know the limitation of Arrhenius. Another flaw in Arrhenius' theory is its reliance on the concept of dissociation of acids. Look at both of these. We did these earlier as dissociation reactions, right? We showed that this is going to literally break apart into that. This is going to break apart into that. And the only thing different with what we did before is we started as a solid dissociating. Breaking apart. We now know that the hydrogen ion, cation, does not actually exist. What? In this form in aqueous solution. What it's going to do is it's going to become the hydronium ion. So we know Arrhenius' theory, way back, super old. It's okay that he got it a little wrong. He's more right than he is wrong. So that hydrogen ion, still going to use it all the time, but it actually in water, it's going to be picked up by a water molecule, H3O plus. Does that make sense how you got H3O plus? Now, let's just think about that water. I'm going to do it here. Remember we did the Lewis structure of water? We have two locations where something else could bond. If we put a hydrogen here, right, it can share one of these guys, right, because hydrogen has one. That'll make one of these guys. And we have a whole other proton. So this is, see how it can be H3O plus? Does that kind of make sense to you guys? Because there's a location for it. Therefore, Arrhenius level theory can only describe acids and bases in an aqueous environment, relies on the flawed concept of acid dissociation, and excludes many substances based on its restrictive definition and generally not used, but you should be able to recognize it. Not used. Turn the page. Bronston-Lowry definition of acids and bases. Now, 1923, Johannes Bronsted and the English chemist Thomas Lowry expanded upon Arrhenius's ideas by broadening the definitions. They centered on the proton, which again, we now know doesn't really exist in water. A proton is what remains when the most common isotope of hydrogen loses an electron. Common isotope of hydrogen is hydrogen 1. This is supposed to be up here a mass number. It's just a bit of a typo. A compound that donates a proton to another compound is called a Bronston-Lowry acid, and a compound that accepts a proton is a Bronston-Lowry base. And yeah, we got that. Using these very simple definitions, the Bronston-Lowry level theory covers the large majority of known acid-base behaviors. Thus, this theory can be successfully applied for most of this course. However, to be inclusive, and we want to be inclusive, to all acids and bases, that we go and we use the general Lewis theory. The general theory is required. The final and most general model of acid-base behavior is by the American chemist G.N. Lewis. No. Acids may be inorganic or organic substances. So hydrochloric acid versus acetic acid, right? This is your organic base. This is your inorganic base. They may be neutral substances or ions. Neutral substance, water. Water can act as an acid, or hydrosulfite. This is an ion. Hydrosulfite ion. Each of these species contains at least one hydrogen atom. And to be defined as a Bronston-Lowry substance, it must be able to donate that atom. So, Lewis. Bronston-Lowry. So Lewis acid. What's a Lewis base? That's what we're going for. That's what we're looking for here. Bases may also be, oh wait, I missed it. What did it say? Each of these species contains at least one hydrogen atom to be defined as a Bronston-Lowry acid, and the substance must be able to donate this atom to another substance in the form of a proton. So a Lewis acid, right? It's a compound that must contain a hydrogen atom, and what? Be able to donate. Oh. For substances, acids may be inorganic, organic, Each of these species contain at least one hydrogen atom. So whether it's this one, this one, this one, or this one, to be defined as Bronston-Lowry acid. And the substance must be able to donate this atom to another substance in the form of a proton. So this is the part, so the fact that all of these have it, and they can donate it to another substance in the form of a proton. Yeah, it's almost exactly the same, right? What makes it different?
It says to be defined as a Bronston-Lowry acid substance.
Must be able to donate this atom to another substance in the form of a proton, comma, but not and.
That thought, but Lewis acids are ones that are defined as electron separate.
But we're not at electrons yet. Oh. That was earlier?
Yeah.
How did I miss that?
It was on the,
If you can imagine rainy, I thought that was coming up.
Yeah, premise it on the first page.
Right.
yeah, it's on the bottom.
Oh, Does the figure show below level theory expansion include
Right.
defines as proton and bases, proton acceptors, which states that acids are pair acceptors, electron pair acceptors, while bases are electron pair donors. Yeah, a compound that must contain a hydrogen atom and be able to donate to compound, another compound. So I see what you're saying. You want me to,
Yeah, I was, because I feel like it's. saying-
you're saying it's too similar to this one.
Like, I feel like it's saying the same.
Okay. Okay, I see that differently, but okay. Because within the compound, you want to keep it the electrons. Okay, so
Oh,
let's,
wait, yeah, I think I see what you're saying now. So like, a acid can be like a Lewis acid and a Bronsted Lowry acid,
uh-huh,
and it can be just the Lewis acid.
yes,
So,
yes. That's why comma, not and. But when it's, I think it'll become clearer when we do some. Okay, and then the Lewis base, how you want to do that? What do you want to do the Lewis base? Bases may also be inorganic or organic. So inorganic, organic methyl, remember methyl is the CH4. So methylamine, this is organic, this is inorganic. Think of organic as carbon-based chemistry, organic chemistry, carbon-based chemistry. Can be a neutral substance. Again, look at ammonia or ions. Here we got a crazy ion right there. Right? Each of these are capable of accepting a proton and may therefore be classified as Bronsted-Lowry bases. But any of the four, so I think of it as these guys are inclusive, meaning you're going to have your ions, you're going to have your neutrals, you're going to have your organics, and your inorganics. Now, on a test, if you see something organic, carbon-based, use Lewis all the time. You see something carbon-based, use Lewis all the time. Now, let's keep going. The most familiar and recognizable bases tend to be your inorganic ionic compounds, the hydrochloric acid, hydrobromic acid, the ones we've been using all the time. The conjugate base of an acid is what remains after the acid has donated a proton. This species is a base because it can accept a proton to reform the original acid. What is it called when you have the arrows going in both directions? Equilibrium. So think of it left to right. If moving from left to right, you remove an acid, this is an acid because it's donating that hydrogen. That's what makes it an acid. And once you remove that, that went somewhere, that went to something else, whatever is left is the conjugate base. Whatever is left is the conjugate base. So it's not the best picture. But if we look down here, if you have, what's this called? Hydrofluoric acid. If you have hydrofluoric acid, and let's say we just put it in water, H2O, it will donate its hydrogen to this water. So we're going to get H3O plus and our, so over here, it acts as an acid. because it's a hydrogen donor, right? What is left is this guy. That's what's left after it loses a hydrogen. This is called the conjugate base. Conjugate base is what's left after it's donated its proton. Does that make sense? Look at me, I just called donated proton. I'm so old school. Are you guys getting this? Yeah, cool. It works the other way too. Conjugate base is what results after it has accepted a proton. So you have a base. Once it's accepted a proton, it's considered a conjugate acid. This guy, your regular ammonia, let's add an H plus because it accepted. So when it's accepting that H, it's acting like a base. But what's left after it accepts is this guy. So that would be the conjugate acid, what it looks like after it's accepted the hydrogen. Before it can take a hydrogen, after it's already taken it. Want to try some? Yeah, this is fun. This is awesome. Oh, wait, there's more to read. Yes, of course. You're going to miss the good part, though. Okay.
So I'll read it on my way back.
Oh, compound. That and accept hydrogen. From another compound. From another compound. In the two schemes above, the behavior of acids as proton donors and bases as proton acceptors are represented in isolation. In reality, all acid-base reactions involve the transfer of protons between acids and bases. This is quite useful when tasked with exercises asking you to classify reactions, such as those done in our past units. We looked for acid bases making salt and water, and we called it a neutralization reaction, right? Well, they're going to get a little more complicated. So this is going to really help us out. If you can identify all four terms in a proton transfer reaction, all four terms, so that's acid, base, conjugate acid, and conjugate base. If you can identify all four of those, then you're good to go for an acid-base reaction. Okay, but you have to be able to identify those. A water molecule functioning as an acid transfers a proton to an ammonia molecule functioning as a base, yielding the conjugate base of water and the conjugate acid of ammonia. So that's this example right here. We have water, liquid water, and ammonia in equilibrium. We're going to add these two together. Our conjugate base of the water as an acid. How do I know the water was an acid? How did NH3 go from here to that? It would have had to have gained a hydrogen. Where did it get it from? The water gave it to them. Right? So the water gave ammonia a hydrogen. So acid is the proton donor. The base is the proton acceptor. Well, what's left after it has lost a hydrogen looks like that. And what does this look like after it's accept the hydrogen? It looks like that. So if you think of this acid base going this way, this is how I learned it. What about going this way? Going this way, this guy, can you see the yellow? This guy donates the hydrogen, right? So if I went that way, this is the acid. And this guy's accepting the hydrogen. So this is the base. So going this way, one's an acid and a base. Going this way, one's an acid and a base. And you can't have double acids and double base, so they made up this word conjugate. But it's really just what's happening going this direction. Now, the reaction between a Bronsted-Lowry acid and base is called ionization. Now, this differs slightly from the term dissociation. So everything this way, we say dissociation, right? Because dissociation occurs when you put that solid in water, right? And that's Arrhenius, he's all about water. Down this way, we call it ionization. Auto-ionization or de-ionization, all of that, we call it ionization. More specifically, when we add acid to water, acid ionization occurs, in which protons are transferred from the acid molecules to the water molecules. So acid ionization occurs when this proton is transferred from the acid to the water. That's acid ionization. For example, when hydrogen fluoride dissolves in water. Yeah, there's the example. When we add a base to water, base ionization reaction occurs in which the protons are transferred from water molecules to the base molecules. So the example for that is this guy. Here's our base. We're adding it to water. So our base here, what does a base do? It's a proton acceptor. It accepts a proton from the water, which makes our hydroxide. And now it's an acid and a base. Does this look familiar, guys? From last time? Why isn't, so this is products over reactants. Why isn't water under here?
Is there like Cincinnati?
Yeah, it's because it's a liquid. Remember, equilibrium constants don't include liquids or solids. And here it's not in solution yet, it's not aqueous, right? So it's considered a liquid. So that's why you don't have to include it. Now, okay, here's my favorite part of the notes. How can you spot the difference between a chemist and a plumber? Ask them to pronounce the word. See, if you see unionized, you're plumber. Versus unionized. Okay. No. Okay. That's the best I got. Okay.
It's actually one of the better jokes.
I don't know how to take that. So, okay. Let me just, so as things get more complicated, it says this link goes over the following. Do you know how to get to your active links in your workbook?
Yeah.
Go back to day one, the PDF, right? Scroll down, click it. And when you see that for all the harder problems, it's literally going over every one of them. But try them on your own first. Try them on your own first. So here it says label the acid and the base if possible. So it's not always possible. Label the conjugate acid and the conjugate base. Highlight the species affecting the pH. Remember, water is amphoteric, which means it acts as an acid or a base. So here we're equilibrium. We have hydrochloric acid in water. This guy is going to donate a hydrogen here, right? It's going to donate a hydrogen here. So what are we going to get on this side? We're going to get Cl minus. And what else? H3O. Don't forget that plus, right? That's what we're going to get. Does that make sense to everyone? Over here, since this is doing the donating, this is the acid, yes? And the water is accepting, so that is the base. Now, We need to do conjugate acid and conjugate base. Is this guy the conjugate acid or the conjugate base? It is the conjugate base. And this guy is the conjugate acid. And if you want to think about it going this direction, if it goes in this direction, this guy would be the acid because it would donate the hydrogen, donate that proton. This would be the base because it would accept it. Yeah. And what would the equilibrium constant look like? Concentration of the chloride ion, which is just molarity, and concentration of the hydronium ion, all over what? Yep, the concentration of HCl. Or, and remember, these are just molarities. They're just molarities. Want to do another one? Yeah.
What does it mean how it just species affecting?
pH is a measure of the hydrogen. So what species is changing the amount of hydrogen in solution? Yeah, this guy would be what would be responsible for changing the amount of hydrogen in solution. Absolutely.
Would it just be on the flat side or just all the Gambia?
No, it would just be on the
Or-
reactant side. Yeah, reactant side. That's pretty easy. That's pretty easy. Let's look at number 4. So here it's a compound that has a hydrogen atom, right? So we're not at Arrhenius, which is up here in water. That would be an Arrhenius kind of guy. But this guy here would be more of a Lewis, right? Because it's organic and has a hydrogen. So this guy will donate a hydrogen ion. So this is the acid, this is the base. What are we going to get on this side? C5, the carbons didn't change, right? H4N, and that's going to make it have a charge, right? Because it's lost a proton there. It's lost a proton. And H3O positive.
How could you tell that the C5 is
And not the H2O to Lewis structure. All the way back to the Lewis structure and yeah, all the way back to stable Lewis structure and remember bonds minus dots? Bonds and dots, sorry. Valence electrons minus bonds and dots. So it's going to favor a more stable dude kind of thing. There's no affinity to pull that off. It would be clear. It'd be clear. It'd be super clear. Absolutely. We have another organic acid here. Organic acid. So what's this guy gonna do? Gonna donate, oh, sorry, acid base. So this is the conjugate base and this is the conjugate acid. Make sense to you guys? Yes. 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 You want to do number 2? Let's do number 2. Water would be an acid here. Water would be an acid here. Remember NH3? Right? So it is totally fine taking another hydrogen right there. Completely fine taking another hydrogen. It's not going to work out losing a hydrogen. Right? It's not going to work out losing a hydrogen without something else going on. Without something else going on. So that means this is the acid, this is the base. I'm gonna get NH4 plus for my conjugate acid and OH minus for my conjugate base. Because if I were to go the other way, the hydrogen's gonna move over that way. Yes,
So in this case, the water would be like affecting.
yes, the water would be what's affecting the pH. Absolutely.
So everything is acid.
Yeah, because it's asking pH. There's also something called POH. It would be the base that would affect the POH. Because it's asking that, yes.
So for number 4, normally the way you identify an acid is if it starts with H, right? So like, how do you know?
That's the
Or Bronston-Lowry even. Arrhenius and Bronston-Lowry. Now Lewis. Lewis is more inclusive. Anything can be an acid if it wants to be. If it's going to act like an acid, we're going to let it be an acid. It can be neutral, it can be an ion, it can be organic, it can be inorganic. We're going to let it act as an acid. I could teach you everything at once if you know. So for homework, you want to finish 1 through 10. 1 through 10 for homework. And little teaser. Could this act as an acid again? The Lewis acid again? Could this act, because ions are allowed to act as acids? Could that act as an acid again?
Just keep doing it until.
It could, right? It could act as an acid again. This little teaser. This little teaser. But he's more, yes.
So why is there an extra space on the break?
Ooh. Uh-huh. 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 Okay. So sodium hydroxide in water. What's going to happen? Well, we're going to get a sodium ion. Yeah. Sodium ion. And then we're left with this. Now, so we can get water and hydroxide ion, right? So we don't have a set conjugate acid, conjugate base here. Right? We don't have a conjugate acid, conjugate base. Now, you might be thinking, guys, and that's great if you are. You might be thinking, well, NaOH and H2O, why didn't this guy just donate its hydrogen, right? And that would make H3O plus and NaO ion. Well, that would then split again, right? So then we'd have Na, and then O doesn't hang out by itself. So then we'd have little water bubbles. But why doesn't that happen? And it does. Maybe 1 in a quadrillion molecules. And it's at equilibrium. So then it goes right back. So it's really what thing is favored? What is actually favored? And remember, how are we going to find out what's favored? Calculating that K. Right? Is it going to lean to the right? Is it going to lean to the left? What's going to actually be favored by calculating the molarity? If we don't get a high molarity of this concentration, then that's not what's happening. Right? So our Ka is going to say, go that way. It's not going to do that because we're not getting a molarity of that because that's not happening. Yeah. It's all going to come together. Just hang on. I know it feels all icky. Yes.
So number 4, when you said that it could like do it again, is
Uh-huh.
that gonna be a conjugate acid? Because it can be still an acid.
I don't know. That would be too confusing for me. That's too far in advance. Once it does it again, it would be an acid and then it would be a conjugate base again. So this wouldn't be a conjugate base would be H3. H3 2 minus. Yeah. Okay, so the rest of class, guys, is lab time. Total lab time. Please don't do your homework now. The rest of class is lab time. You got some math to work on. You got some looking around to do. Now, do not expect to be able to do this now, right? You're exploring your capabilities. Exploring your capabilities. I have everything out that you could possibly need to be able to see sig figs and what you could measure and what you can do. And like it says in Schoology, you're using a dihydrate, so you can come up and look at the formula weight, which you know as molar mass. Figure out what you think you can do. Don't watch the video. What video? Oh, that one. Oh, gosh. No, you start at 44 minutes and he's actually going over the aluminum and copper 2 chloride. No, you just watch how he calculates with molarity that one problem. Like 2 minutes worth, maybe 2.5. So formula weight is what you know of as molar mass. 170.40. No, it says copper 2 chloride, dihydrate lab grade. That's the formula. Done. Dihydrate, because you have to add the mass of 2 water molecules, and that's how it gets to 170.48. See how it looks like it's kind of a little wet? It's not like a real dry powder. You know? So it's there's water molecules associated with those crystals. So you have to, when you're weighing it out, you're weighing out water too. Please do the practice. Don't skip the practice. The practice really should show you something. Whew. So get out the paper and yeah, that's about I think all the countries are a little different. If you wanted to do 12, if you wanted to do that would be fun. That might be easier or you could add it all up. Cover and chloride and water. Recraft this calculation. See what you get. Think about making that solution. Yes, you may. It's a good time for a Jolly Rancher. No, if you need any help. And Abby, remember your partner, the new guy? Yeah. So you're Abby's partner. Yes.
I just have a question about.
No. Yeah. What?
So I was doing a bunch of these films the other day, but I realized I actually never worked this out. I was wondering if you could go over how we calculate.
You need to learn the lab time again. Lab time's important.
I understand that.
So if you have a lab question, I'll help you with a lab question, not a work one. So, okay. Talk to me about the lab, not the work.
Okay, so when you calculate mass
Max.
for, when you have your volume and you have your calculate
Okay, so you have the molarity.
or increase 10 milliliters of volume.
So that would be, so,
0.01.
but the first thing I asked you to do was just how would you make of that molar solution?
Right.
That's mole over liter, right? And mole over 1 liter. So that means you would do 0.01 moles of CuCl2. But don't do that. 2H2O. Yeah, don't do that. And don't do it. Write it the way. Okay. So how many grams is that? You're just gonna multiply by the molar mass. 1 mole is how many grams? 170.45, I think, grams. Right? So when you multiply, so what I asked you to do was do the 3 different molarities. 0.01, 0.02, and 0.03
Okay.
molarities, right?
Okay.
And you get moles. Then remember the reaction. You're doing aluminum and copper to chloride. It's gonna make aluminum chloride and copper, right? So when we balance this, so this is mole of CuCl2, right? Then you can multiply by the mole ratio, which is what, 2/3? 2/3. And then now you're talking aluminum, and then you can multiply by 26.98. You could get your grams of aluminum for each one of these, right? That should help you think. When you get those answers, that should help you think. Okay, so first, calculate moles for each one of these. How many moles of copper chloride you have, right? And how many grams you have to have in a liter,
Okay.
right? And then you can cut it down. Well, we're not gonna do a liter, we're gonna do 10 mils. So then cut that down,
All right.
right? So it walks you through it.
All right. Thank you.
This is you. You are in control. Where does sig figs come from? Mars, Venus, where? Where do they come from? No, no, no. I have equipment.
Oh, yeah,
Come from what you're using, right? You're gonna use this. How many single faces, one more than the line that has on, balance. Depends on what you're using. Not sure you're doing it. Right. No, that's why I asked you to read it when you were done with the formulas and ask questions.
Well, I thought I got it, but then.
Okay,
I said,
so what's your question?
So,
Don't get the wording, ask me what you want to know.
just, like, typical of, like, you want all of the copper pieces.
Right, so copper needs to be the limiting reactant.
Okay, so all of it needs to be reactive.
Copper is the limiting reactant,
Okay,
right? So
Yeah.
that's the whole theoretical,
okay,
right? Because you can't go any further than once the copper's gone.
alright.
That's the end.
So what is the not fluid is that like copper chloride dihydride?
Dihydrate.
I don't know what that is.
Well, look at the bottle. No, it's not. You can. Oh my God.
Oh, dihydrate.
Okay, you obviously need to take your time to read multiple lines. FW stands for formula weight, which is the same as molar mass. The weight of the formula is molar mass. So if you do become a chemist, don't think you're going to have to calculate molar masses the whole time. Every time it is. Now, you still rounded the molar mass.
I know, but I got pretty back.
Okay. Oh, okay. Gotcha. Oh, I get you. I hear what you're saying.
We're not using precise.
Yeah. Yeah, you're right. You're right. So your question is, what exactly is the formula? Okay, so you're gonna take the CuCl2 2H2O, okay? And that's what you're going to mass and put in a volumetric glass, right?
What is that done?
That is associated with. That means for every one of these crystals, two water molecules are in the crystal, will have a sequence. It's not multiple, right? We've done this before. Yeah, you add all of that up. Yes, fine, yes. So this is gonna go into here, right? You're gonna have your pile down at the bottom, and then you're gonna fill it up with what? Water. Okay? Does that make sense? So then you're gonna use that. So you're really only using this, right? Because these are gonna get lost in all the others. So the formula still is, you're adding aluminum to CuCl2, and we're gonna get aluminum Cl3 and copper. It's still the same thing you did before. Right? It's still this. You're still gonna refer to this for your stoichiometry.
Just ignoring the dihydrate.
Okay, no, you're not. Okay, so are you ignoring the dihydrate? No, you have to take the dihydrated into account, but you're making a solution, right? You're making a solution with it. So those water molecules get mixed with these gazillion water molecules. So what's actually associated in here is your copper and your chloride ions, right? The rest is water. Right? This is really what's involved in the reaction, and that's what's represented right here. And you're just gonna then add also aluminum. So you can drive by there. Because, yeah, where's the water in this equation? Right, so, but you're not putting H2Os in there.
Yes.
See? Oh my gosh.
Just that section. What do we talk about?
The whole thing. And then,
What's that?
and then you gotta see if you can actually mass it on the balance.
Yeah, right.
I have a question about this one over.
Uh-huh.
So I watched one of the videos on Twitter, and there's like a very similar plot of like cesium, and diamond silver and everything else like that. So there was a very so on the machine was installed.
You said no. Mind taking me an email, like to that point where it's straight over. Just a quick note. Bye, guys. Get outside. It's a beautiful day. How are you? You're so quiet. You were, or at least with me. Seemed a little. I mean, you were cool and all. It just seemed a little quiet. So I was just checking on you. I am excited about the warm weather, actually. And they mowed out front, and I was like, oh my god, I love the smell. Mowed grass. It was actually kind of cool. So
My parents, I bought a house, and so now we have to like mow the lawn. I've never done that before, so I'm very excited.
yeah, it's fun. And you can plant flowers and stuff. Yes, you may.
And with the snow, they like close, but they still like ready.
Yeah,
That's like
that's super cool. You too. Oh, do I need to turn that on for you, sweetie? Is it accepting? Okay, cool. I just need to send this email. Take me a bit, so give me a few minutes, like 5 minutes.